Today, we are tackling, well, maybe our biggest topic yet. We're diving into the nature of reality itself, space, time, how we've thought about them, and where physics is taking us now.
Yeah, it's a huge one because, for ages we've pictured space and time as smooth, continuous things, like a backdrop. But the sources we're looking at today, they suggest that whole picture might be, well, fundamentally wrong.
An illusion, almost, which sounds pretty wild.
It is wild. We're exploring this idea that deep down there's no continuous space or time at all.
And just to give you a sense of how mind-bending this is, there's this great story about the physicist Carlo Rovelli. He was trying to figure out how to structure a book explaining this exact idea, a world without continuous space and time.
Right. This was back in 2012.
Right.
He's driving alone, Italy to France, and suddenly, boom, the whole structure hits him. He gets completely caught up in it, mapping out the book in his head.
So caught up, he starts speeding, like really speeding.
Yeah.
And naturally, he gets pulled over by the Italian police.
Uh-huh. And Rovelli, apparently still buzzing from this insight, tells the policeman, I just figured out how to write my book. It explains how space and time aren't smooth. They're like grains of sand.
And the policeman's reaction, he just listens, wishes him good luck with the book, and lets him go. No ticket.
It really captures the feeling, doesn't it? This isn't just dry physics. It's a radical rethinking of everything.
Okay, so if we're losing continuous time and space, where did this whole journey start? How do we even begin thinking about what reality is made of?
Well, you have to go way back. Before science, really. Early explanations were all myths, right? Gods, spirits, giant creatures, plumed serpents, great cows, bringing order out of chaos.
Divine commands, basically. Fiat lux.
Exactly. But then, around the 5th century BCE, particularly in places like Miletus and Ionia, something shifted. Thinkers started looking for natural explanations.
And this leads us to the atomists.
Precisely. Leucippus, and especially his student Democritus, they came up with this absolutely beautiful idea, atomism.
Their idea was, what? That everything is made of tiny, indivisible particles. Atoms.
Yeah, atoms moving in empty space, the void, and all the amazing variety in the world, trees, people, rocks, everything. It's just down to how these atoms are shaped, how they're arranged, how they're ordered.
Like letters of the alphabet making different words, comedies, or tragedies.
That's the analogy they used. And crucially, Democritus had a logical argument for it. He said, look, you can't divide matter infinitely.
Why not?
Because if you could, you'd eventually end up with points. Points with no size, no extension. And how can you build something with size by putting together things that have no size? You can't.
Ah, okay. So there must be a smallest bit, an indivisible piece, an atom.
That's the logic. Pure thought, no experiments. It's why Feynman famously said, if all science was lost, the one sentence worth saving is the atomic hypothesis. Everything's made of atoms in motion.
Such a powerful idea. But just an idea for a very long time.
A very long time, like 2,300 years before we got actual scientific proof.
And that proof came from Einstein, right?
Yeah.
In his miracle year, 1905.
Yep. Young Einstein, 25 years old, working in the patent office. He wasn't looking at atoms directly. He was looking at Brownian motion.
That's the random zigzagging. Pollen grains in water, stuff like that.
Exactly. Robert Brown had noticed it decades earlier. Einstein figured out why they jiggle. It's because they're being constantly knocked around by the water molecules themselves.
But why does that prove the molecules are finite, atom-like?
Because the knocking only works if the molecules are discrete things, hitting unevenly. If water was infinitely divisible, a smooth fluid, the pushes from all sides would perfectly cancel out instantly. The pollen grain wouldn't move.
So the fact that it does wobble means the molecules hitting it must be real, finite things, atoms.
Precisely. And he used the math to work back from how much it wobbled to figure out the size and number of these molecules. Democritus's atoms finally measured.
Okay, so atomism gets proven, but physics was also looking at the big picture, right? Gravity, planets.
Right. Centuries before Einstein, you had Newton. Huge leap. He connected Galileo's work on falling objects here on Earth.
Everything falls at the same rate, roughly 9.8 meters per second squared.
With Kepler's laws describing how planets orbit the sun, Newton wondered, what if the force pulling the apple down is the same force holding the moon up?
His thought experiment with the cannonball, the little moon.
Yeah, imagine firing it faster and faster until it orbits the Earth just above the mountains. He calculated its acceleration towards Earth, and guess what?
9.8 meters per second squared.
The exact same value. It proved the force was universal. Gravity wasn't just an Earth thing, it was a cosmos thing. It unified heaven and Earth, breaking that old Aristotelian divide.
But Newton's gravity was still, particles pulling on particles across empty space, right? Instantaneously.
Yes, action at a distance, which bothered some people. And then came another huge conceptual shift with Faraday and Maxwell. Electricity and magnetism.
They introduced the idea of the field. That sounds important.
It was revolutionary. Faraday, experimenting, got this intuition that forces weren't acting mysteriously across space. They traveled through something real, something physical he called lines of force, filling space.
So not empty space anymore.
No. And Maxwell took Faraday's ideas, these lines of force, and turned them into elegant equations. And those equations revealed something astonishing.
Light?
Light itself, it turned out light is just a wave, a ripple, a trembling in these electromagnetic lines of force. The field became a fundamental entity as real as particles.
Okay, so we have particles and now we have fields. This is getting more complex. And this leads us back to Einstein again.
Back to Einstein. First, special relativity in 1905. It messed with time. Showed time isn't absolute, it depends on your motion.
And it introduced that idea of the expanded present.
Right. For any event happening far away, like on Mars, there's a period, maybe 15 minutes from Mars, that is neither strictly in your past nor strictly in your future, because information can't travel faster than light. That delay isn't just technological, it's built into the fabric of space-time.
Okay, so time gets flexible.
Hmm.
But then, general relativity in 1915. That was even bigger. He merged gravity with space-time. How?
He realized space-time wasn't just a fixed stage for things to happen on, it is a thing, a dynamic, flexible thing, like a giant mollusk was his image.
A mollusk, okay.
And gravity isn't a force in space-time. Gravity is the curvature of space-time caused by mass and energy.
So the Earth isn't being pulled by the sun bends space-time around it.
Like a bowling ball on a rubber sheet.
And the Earth is just rolling along the straightest possible path in that curved space, like a marble in a funnel.
Exactly. And this crazy idea made predictions that turned out to be incredibly accurate, like the tiny extra bit in Mercury's orbit that Newton couldn't explain.
That 0.43 arc seconds per century.
General relativity nailed it. And more recently, we've directly detected gravitational waves, ripples in space-time itself, predicted by Einstein a century ago.
So general relativity gives us this beautiful picture of a smooth, curved, dynamic space-time for the large scale.
Yeah.
But we started with atoms, granularity. Did that idea apply elsewhere?
It absolutely did. That same year, 1905, Einstein also showed light energy comes in packets, photons, based on Max Planck's earlier work.
So not just matter, but energy and fields are granular too, quanta.
Yes. And this kicked off quantum mechanics. People like Bohr, Heisenberg, Dirac developed this new physics for the very small, and it was weird.
Weird how?
3 key things. 1, granularity. Information is finite. There's a limit, defined by Planck's constant, $2. Nature is pixelated at the bottom.
Okay, 2.
2, indeterminacy. The future isn't fixed. You can only predict probabilities. Where will an electron be? You don't know for sure, only where it's likely to be.
And 3, this is a really strange one, isn't it?
3, relationality. Things only seem to have definite properties like position when they interact. Heisenberg realized a particle might not have a precise position until you measure it, until it bumps into something else.
It exists as a haze of possibilities until it's forced to choose.
Sort of, yes. Properties emerge from interactions. The world is fundamentally about relationships.
Wow, okay. So now we have these 2 incredibly successful theories. General relativity for the big, smooth, curved stuff.
And quantum mechanics for the small, granular, probabilistic stuff.
But they don't play nice together.
Not at all. That's the schizophrenia of modern physics. They are based on contradictory principles. Continuous versus discrete. Deterministic geometry versus probabilistic interactions.
And where does this clash become obvious?
In extreme situations, like the very center of a black hole where GR predicts infinite density, a singularity, or the very beginning of the universe, the Big Bang. When you try to use both theories there, the equations just break. They spit out infinities.
Which means the theories are incomplete? Something's missing.
Something fundamental. And the obvious thought is, if space-time is the gravitational field, as Einstein showed, and if fields are quantum, as Planck and Einstein showed,
then space-time itself must be quantum. Granular. Probabilistic.
That's the unavoidable conclusion, and that's the quest for quantum gravity, to find the theory that unifies them.
And this quantumness of space would only show up at incredibly small scales, right?
Unimaginably small. A physicist named Matvei Brennetin figured this out way back in the 1930s. He saw that combining GR and QM implies a fundamental limit, a shortest possible length, the Planck length. About 10 to the minus 33 centimeters.
Okay, numbers that small are hard to grasp. Give me an analogy.
Okay, if you blew up a single atom to be as big as the entire observable universe, the Planck length would still be smaller than a tree on that scale. It's the absolute pixel size of reality.
So below that, the idea of smooth space just dissolves.
Completely. And this brings us to one of the main candidates for quantum gravity, loop quantum gravity or loop theory.
Loop theory, what's the core idea there?
It takes Einstein's spacetime and Faraday's lines of force seriously, but makes them quantum. It says space isn't continuous, it's woven from finite loops or threads of the gravitational field itself, quantized lines of force.
Like a fabric.
A quantum fabric. These connections form networks called spin networks, and the crucial result from the theory is that properties like area and volume aren't continuous either. They come in discrete steps, meaning there's a smallest possible chunk of volume, an atom of space. You can't have less volume than that. Measuring the volume of this room fundamentally means counting how many of these Planck-sized grains of space are in it.
That's mind-blowing. Counting space itself.
It is. And it has profound consequences. The biggest casualty? Probably our familiar notion of time.
How so? If space is granular, what happens to time?
The smooth, universally flowing time of Newton, that single t variable in equations, it disappears at this fundamental level because the quantum gravitational field, the fabric of space-time, is fluctuating probabilistically. There's no stable background clock.
But wait, I mean, we experience time flowing. Things change, we get older. That feels very real.
Yeah. It feels real, yes. But loop theory suggests that flow is an approximation, something that emerges at larger scales, maybe linked to thermodynamics, heat, what's sometimes called thermal time. Fundamentally, the world might just be relationships between variables, how things change relative to each other, not relative to some absolute flowing time.
So the smooth reality we see, the steady passage of time, it's like watching a movie. It looks continuous, but it's really made of individual frames flashing by.
That's a decent analogy. The underlying reality is this quantum foam, these spin foams, which describe the probabilistic evolution of the spin networks, the atoms of space. It's this incredibly complex, dynamic dance of quanta that, when blurred out on our macroscopic scale, looks like the smooth spacetime of Einstein.
Okay, so let's try to sum this up. The picture emerging is, reality is fundamentally made of quantum fields interacting. And what we perceive as continuous space and time are just large-scale averages, our fuzzy view of this grainy quantum world.
That's the essence of it. It's a radical shift. But the payoff is potentially huge. It could mean the end of infinity in physics.
How does it end infinity?
Because introducing this minimum length, the Planck length, acts like a cutoff. Just like special relativity introduced a maximum speed, the speed of light, and quantum mechanics introduced a minimum chunk of action, Planck's constant dollars. Quantum gravity introduces a minimum length, Elf's dollars. Those infinities that pop up in GR at singularities or in quantum field theory calculations. They might disappear because space itself can't be infinitely divided.
Nature abhors infinities, maybe. Infinite is just what we call something we haven't measured properly yet.
That seems to be the lesson. And this leads to maybe the most exciting, most provocative idea of all, related to the Big Bang.
If space has a minimum size, the universe couldn't have been compressed into an infinitely small point at the beginning.
Exactly. The idea of the singularity might be an artifact of using the wrong theory, GR, at that scale. Quantum gravity suggests something different. A big bounce. Yeah, the universe contracted down to the Planck scale, incredibly dense. But the quantum nature of space itself resisted further collapse, a kind of quantum pressure, causing it to rebound violently into the expansion we see today.
So the Big Bang wasn't necessarily the beginning, but maybe just a transition from a previous phase.
It's a possibility opened up by the theory. And the amazing thing is, this isn't just pure speculation anymore. Scientists are looking for evidence.
Where? How could you possibly see evidence of a big bounce?
In the cosmic microwave background radiation,
Right.
the CMB, that's the oldest light in the universe, a snapshot from when it was about 380,000 years old.
Okay.
Well, the big bounce scenario, particularly within loop quantum gravity, makes specific predictions about the statistical patterns, the tiny temperature fluctuations, in that ancient light. People like Ashtekar, Golo, Nelson have calculated there might be specific subtle signatures, maybe a slight anomaly on the largest scales, that wouldn't be there if it was a singularity.
So, by studying the faint afterglow of the early universe, we might actually find proof that space itself is granular and that our universe bounced.
That's the hope. It's right at the edge of what we can measure, but the search is on. Finding the evidence would be revolutionary, confirming this whole new picture of a quantum granular reality, and maybe even telling us what happened before the Big Bang. That's where the frontier is right now.